Welcome friends. So today we'll be discussing how to use Clapperons 3-moment theorem for a continuous beam with like fixed end support, or like if it has a cantilever portion, then how to deal with those kind of problem. So say this is like ABC is a beam which has like one end fixed, and at the other side it has a cantilever portion or overhanged portion. Then how to solve this kind of problem using Clapperons 3-moment theorem, or how we can fit the Clapperons 3-moment theorem for this kind of problem, since Clapperons 3-moment theorem needs to consecutive span, right? So here we need to do two adjustments. First adjustment is that this fixed end we have to convert into a imaginary span of zero length. So what I'm telling here, like say there is a span which has like fixed support, like this is given, right? This is B, this is A, this is C. So instead of this now A fixed support, what we have to do, we have to introduce an imaginary beam. This is like say A0, this is A, this is B, and this is C. So this is like an imaginary portion that we need to assume, and the length of this imaginary portion is 0, since there is no as such any length, but then we have to assume this as an imaginary span. So this is the first adjustment that we need to do. Instead of fixed support, we have to consider an imaginary span of length 0 length, right? And then we can use this Clapperons 3-moment theorem for this two span. No doubt length is 0, so we'll substitute length is 0, or like all corresponding values we'll substitute in Clapperons 3-moment equation. But then instead of fixed support, we have to assume this imaginary span. And this cantilever portion, like we can apply the moment, what are the moment that develop in the cantilever portion, that we can apply. Another thing, like this fixed end also develops this moment, and the continuous end also develops moment. So that's how this two will have the same effect finally. Like if you see this AB portion, this is also developing a moment, and due to continuity there is a moment. So that's how instead of like fixed support, we'll convert it into the additional span with 0 length. So these two adjustments are need to be done. First adjustment, in place of fixed support at A, will introduce an imaginary 0 span A0. So like that is what A0. And second adjustment, convert the cantilever portion BC to a point load and a moment. So for that, what you do, you draw free body diagram of this overhang portion, and like if you draw this overhang portion, then the moment will develop at B. This moment will be like 6 kilonewton meter. Simply like you use condition of equilibrium, summation Fy. If you do, you'll get this vertical reaction VB, say VB1 or like maybe VB2. This is VB2. So this like what are the reaction will develop, that like we can calculate here using condition of equilibrium, and those reaction you can apply on the portion BA. Right, what are the reaction we are getting in BC portion, that we have to apply on BA portion, right? So like this 6 will be 6 here, this vertical reaction will be upward, since here it is upward, so it will be downward here, right? And then we have to plot bending moment diagram of release beam, since we already discussed why we need this bending moment diagrams later on. So assume that each span is like a simple support span, or like say there are hinges at each joint, and then we are plotting this bending moment diagram. So like since this is 0 span, there is no load, so there won't be any bending moment in A0A portion. And then for this portion there is there is UDL, and then if it is simply supported, then the bending moment diagram will be a parabola. So like maximum ordinate of this parabola will be like WL square by 8. So W is the intensity 12, L is the span 6 meters, so 6 square by 8, and it comes out to be 540 kilonewton meter. See, right? So this two adjustment needs to be done, and once we do this two adjustment, then easily we can solve the problem, right? but then we have to use this Clapperons 3 moment theorem for this imaginary span A0A and AB, since now we have this two continuous like beam, or this is like a continuous beam which has two adjacent two span, right? So this span and this span are like adjacent two span, for which we'll be using Clapperons 3 moment equation. So I'll quickly revise what is Clapperons 3 moment equation that we have already done. So Clapperons 3 moment equation, like if there is like beam or continuous beam, and in that continuous beam we can use this Clapperons 3 moment theorem for two consecutive like span. So say if there is a beam, so continuous beam is the beam which is supported more than two supports. So like here it is supported on three support. So say this is A, B, C. So like for any two consecutive support we can use this Clapperons 3 moment support. So you can use for this two, or for this two, or for this two. So like say we are using for this two, A, B, C, or AB and BC span, right? So for this two consecutive support. So this is my like now left support, this is my middle support, this is my right support. Like if you are using for this two, then this A0 will be the left support, then this A will be, this will be left support, this will be middle support, and this will be right support, right? So MA is a bending moment at support on left, right? So like if you are using for this three span, then the moment on left support is called MA, right? Then so like I'm using again, I'm drawing it here. So this is A, B, C. So this is my left support, then middle support, and right. Mid, left, right. Okay. Right. So MA is moment at left support, MB is moment at mid support, and MC is moment at right support. So then L1 is the span length of left support, L2 is the length of right support or right span, not right support, right? Then area, A is represent area of free bending moment diagram on right support. So what is free bending moment diagram? Say if it has some like point load and this has some UDL, say, so the bending moment diagram that you have to plot by considering this portion as a simple support. So like you introduce hinges here, or you take this portion separately and assume it is just simply supported by two vertical support, and for the given load we have to plot bending moment diagram. So that is called free bending moment diagram or released beam bending moment diagram. So say whatever may be the load, and then we are getting this two bending moment diagram. So the area of this left bending moment diagram is A1, area of this right bending moment diagram is A2. Then the x1 is the centroidal distance of this bending moment diagram or bending moment diagram on left support from left end, and then x2 is the distance of this second or right bending moment diagram from right support, right? So that is what now we have to use this like for this beam, right? We'll be doing it for this beam, okay? So now MA will be the bending moment at right support, sorry, left support. So left support is A0 because we are using this Clapperons 3 moment theorem for A0A and AB, these two consecutive beam. So like left support is A0. So MA will be the bending moment at A0. So that is what MA is the bending moment at left support, which is like MA0, and it should be a 0 since it is simply supported. Like we have assumed it is simple support and it is ain't simple support, so there won't be any moment here, right? The next MB is the bending moment at mid support, so now it is like bending moment at A. So MB will be bending moment at mid support, and that is nothing but MA. So which like we need to calculate that value, or it is continuous support, right? So it is continuous support, so we need to calculate that bending moment. Then right support, now right like MC. So like we are writing MC for right support, and which is equal to the bending moment at right support. Now right support is B, so it will be M capital B is equal to -6. We already calculated it, right? From like when we draw this free body diagram, then we can calculate this MB. So MB, which we already calculated from cantilever portion BC, so you can calculate it, right? Now A1, area of bending moment diagram of left span, but since there is no load, there won't be any area, and that's how it is 0. And then for A2 is the area of free bending moment diagram of right span AB. So for right span AB, so it will be area of this parabola, which is equal to 2/3 base into height. So 2/3 base is like 6 meter, height is 54. So it is just simply like a cantilever, UDL load. So for UDL load, it is parabola, and the maximum ordinate is 12 WL square by 8. So WL square by 8, W is 12, that is intensity of UDL. L is a length, which is 6 meter, so 6 meter square by 8. So if you calculate, it will be like a 54. So that's how height of this parabolic shape will be 54. So 2/3 base into height, and then it comes out to be 216 kilonewton meter square. Then x1 is the centroidal distance of left span free bending moment area. So for left span there is no bending moment diagram, so like x1 will be 0, and x2 is the centroidal distance of right span free bending moment diagram area. So for right span, like CG, since it is symmetric figure, so CG will be at the mid span, which is 3 meter, so it is 3 meter. L1 is the length of the left span AA0, which we are saying it is 0, and then L2 is the span length of right span AB, so it is 6 meter. So we'll substitute this all value into this 3 moment equation. So if you substitute this value, like A0, MA0 is 0, so like I am substituting here like this is the equation we have, right? So this is like our MA0, so which is 0, so I am substituting that. Anyway, length is also 0, so I have substituted that, plus 2 into MB small b for mid support. So then instead of that, like we'll have MA moment, so MA plus L1 is 0, L2 is 6, plus moment at right support, that is B support, so it should be capital MB. So that we know, we'll substitute that value into L2 is like 6 and minus 0, this bracket, this portion becomes 0 since area is 0, this distance are 0, so this becomes 0, and then this portion 6 into A2 we already calculated 216, that is area of bending moment diagram of right span, this bending moment diagram area. So just we calculated that, so that is 216 multiplied by x2 bar, which is 3 meter, that also we calculated. So we'll substitute that, and even the value of MB, which we already know, that value will substitute here, and then we can solve it, so we can get the value of MA equal to minus 51 kilonewton meter, right? So minus 51. So like if you substitute or if you represent that moment here, see now we are not showing that MB moment here. Why? because we are not plotting free body diagram of this portion. But if you draw free body diagram portion, then that internal moment will come, right, which we already calculated. For example, like here it is free body diagram of say AB. So free body diagram of AB span, then this moment is there, 51 kilonewton meter. This vertical reaction we need to calculate, this UDL load, this VB1, and now this moment is coming. When you draw free body diagram, then whatever the moment that is getting transferred from BC portion to BA portion, that we have to represent, and which is like 6 kilonewton that we already calculated. And when you draw this like a free body diagram of BC portion, that time we have to show the bending moment that is getting transferred from AB portion to BC portion, so which is 6 kilonewton. This two will be always same since it is continuous beam, right? So this moment, so and the vertical reaction here is VB2. So now using conditions of equilibrium for this two span, easily we can calculate this two reaction, this vertical reaction and this moment already known. So like if you use for condition of equilibrium for AB span, then what we'll get is VA plus VB1 is equal to total downward load, which is like load due to UDL. So 12 into 6 will be the total downward load, which is 72. Now we take a bending moment about say point B, and for reaction calculation you are free to assume either clockwise or anti-clockwise, positive or negative. So here I am using say anti-clockwise negative, clockwise positive. So then moment, this is anti-clockwise, minus then VA into 6, this will be like anti-clockwise moment, sorry, this will be a clockwise moment, like this will be clockwise moment. So VA into 6 meter, then this moment due to UDL, so UDL will try to rotate it like this anti-clockwise direction. So minus 12 into 6 is the load into the centroidal distance, so which is 6 by 2 plus this moment. We also need to consider this moment since it is moment, not a force. So for moment we don't need to multiply it by distance, so this portion will come. So 6 is there, and this summation should be equal to 0. So if you simplify that, you'll get VA equal to 43.5 kilonewton upward and VB1 equal to 28.5 kilonewton upward. So total vertical reaction at B portion will be equal to VB equal to VB1 plus VB2. So then VB1 we calculated 28.5, VB2 we already calculated, or like this portion, like you use again condition of equilibrium, this portion you use condition of equilibrium. So total downward force should be equal to total upward, so downward is 12 into 1 meter, so this vertical reaction should also be 12 kilonewton. Okay? So that's how I'm written 12 here. So total vertical reaction will be 40.5 kilonewton upward. So total vertical reaction at B, like if you are writing this portion, then here this vertical reaction is here it is written. So this vertical reaction is 40.5. But if you consider this span separately and this span separately, or if you try to draw free body diagram of this span, that time the vertical reaction, this vertical reaction here will be 28.5, this 28.5 for this portion only, and for this portion the vertical reaction is 12. So together this total vertical reaction will be 40.5 kilonewton. Now next is shear force bending moment calculation. So this is the sign convention, left to right, upward force positive, downward negative, and right to left, downward positive, upward negative, right? So we'll start from this end and we'll go on the right side. So we'll calculate shear force from left to right. So when you are on like say left hand side of point A, there is no like vertical force, so bending shear force will be 0. But if you cross this point, then you will get this vertical reaction which is upward, and we are calculating left to right, so that's how it is positive 43.5 kilonewton. Then at any distance x, why I'm calculating it? Because I can see that this is UDL, so there will be a point where the bending shear force will change its sign, and there I'll get the maximum bending moment, right? So like at any distance x, if you calculate shear force, then say we are calculating it from left to right. So left hand side we have this one reaction 43.5 kilonewton, and then the UDL, there is no any other force. So load due to UDL will be 12 into x, because we are calculating at any distance x, right? And then vertical reaction is 43.5. So sorry, this is the equation. Now to calculate point of contrast shear, this shear force should be 0. So we are just like writing this mx shear force equation at x distance equal to 0, and from that we can calculate x equal to 3.625 meter. So from this end, the shear point of contrast shear is 3.625 meter. So then we calculate it. Now shear force at B on left hand side, so like it will be this vertical reaction and this total downward UDL. So that's a 43.5, that vertical reaction here, and then this UDL load, which is 12 into 6. So again we are calculating it from left to right. So then it comes out to be minus 28.5. So shear force on left hand side of point B is 28.5. This is nothing but like VB1. Then on right hand side, like definitely it should be equal to 12, that is a VB2. Like this VB1 and VB2, whatever we are calculating, same value you should get as a shear force at like B on left and right. And then at point C this should be 0, right? So like then you just put those points and then you connect them. Since it is UDL, the variation will be a inclined line. So that's how. Then that's how we can calculate the shear force diagram. Now bending moment diagram. Since like bending moment diagram as such we don't need to calculate, we already have this like mu and mu dash diagram, or like you simply superimpose like this diagram. This is also called like a mu diagram, right? That we already discussed. Mu diagram, free bending moment diagram, or release beam bending moment diagram, right? So like on this we have to superimpose all positive negative moment. So then at point A on left hand side of point A there won't be a moment, because this is at A. So like we are talking some moment on left hand side of A point, but there is no moment, so it will be 0. But once you cross, you have to consider this moment. So it is minus 51.5, because like this moment will try to rotate this end down, right? It will try to rotate end down, or it's like a hogging moment. So 51 kilonewton meter. Then at a like mid span at point D, so like again this moment will be there minus, and then moment due to this vertical upward force, so it will try to rotate it up positive, or like sagging moment. So that's a 43.5 into 3, this 43.5 into 3, because we are calculating at midpoint, then minus due to this UDL portion. So like this length is 3 meter, so 12 into 3 square by 2. So if you do that, like what the bending moment will get is 25.5 kilonewton meter. Then maximum bending moment. So we already know the point of contrast shear. So below that point of contrast shear only we'll get the maximum bending moment diagram. So point of contrast shear is at a distance 3.625 meter from left support A. So like we are calculating that again, instead of 3, just you substitute now 3.625. so if you substitute that, what value we are getting is 27.84 kilonewton meter. And then the bending moment at point B, which is minus 6 kilonewton, we already calculated that, right? And then at C it is 0. So at B we can calculate from say right to left. So it is cantilever portion. so it will cause like negative moment, so minus 6 kilonewton and C. So again you connect them, you like this already discussed, but then this is the bending moment diagram of release beam. So it is parabola, and then whatever the bending moment you get because of fixity, that you should represent and you should connect them. So finally this is the bending moment diagram that we get. So here you can clearly understand the maximum bending moment is not below or midpoint, it is below this point of contra shear, and it is at a distance of 3.6 meter with the value 27.84. Since like in the beam this maximum values are important because we need to design a beam for these maximum values, so we really need to calculate these maximum values in the beam. So that's the end of this class. Next class we'll discuss one more problem when there is a like a change in moment of inertia of the section, and if there is a settlement of any support, then how to deal those kind of problem when we are analyzing continuous beam using Clapperons three moment theorem. Thank you.